Welcome, this is lecture number 47. In today's lecture, we are going to talk about boundary control techniques and selection of switching surfaces. So, here first we will talk about the switching control law and what are the performance objectives and what are the motivations. Then we want to visualize trajectory and time domain behavior in switch mode power converter. Then we talk about selection of switching surface, like we will talk about first order surface, then higher order surface, and then we want to discuss some switching surface like a trade-off, like a performance, complexity, cost trade-off. And here for first order switching surface also we are going to consider few MATLAB case studies. So, first we have to make our motivation clear. So, if we take as DC-DC converter or switch mode power converter, here I have taken a buck converter example, but you can take boost converter or any other hard switch converter. So, the first objective, we need to achieve very fast transient response, and this transient can appear this transient. So, there can be load transient, there can be reference transient, and there can be supply transient. We are primarily interested, this load transient is very critical, because if we are talking about low voltage high current application where there can be frequent load transient and the step size can be quite large. If we consider reference voltage transient, and there are many applications like a dynamic voltage scaling application, even if we talk about the DC bus voltage, DC link voltage, if you want to change, then the DC link voltage, it may be the output of one converter, so that we need to change. That means we need to change the reference voltage. That means if we talk about a cascaded converter like a for constant power load, like for 40 to 1 volt application, where there is an intermediate bus converter which can be a normal buck converter or it can be an isolated converter, and then followed by multi-phase converter. So, in the first stage converter, when you want to optimize the DC link voltage, then you need a reference transient for the first stage converter. Similarly, for the load stage, if we want to change the VDD of the digital processor, then we need to do supply transient, reference transient for the second stage. So, this is also very critical. And the supply transient also is very important, because we need to reject the disturbance in the supply, so that output voltage should not be affected by the change in input voltage. That is one of the objectives. Now, the load transient and reference transient, particularly load transient, can happen frequently, very frequently. In fact, in industry, when we the industry, when they design a power converter or PMIC, power management IC, let us say for VR application, voltage regulator, right. So, if the switching frequency of the converter is 1 megahertz, so they can test the load transient in some orders of tens of kilohertz and even up to 100 of kilohertz, even for feasibility, like whether the converter will sustain or not, they can even go very close to the switching frequency just to check whether the converter survive or not. But the converter cannot respond beyond a certain frequency of the load transient, and control will play a significant role, that how fast load transient we can cope up using the converter. That means only by increasing switching frequency may not be the only solution. So, here control can play a significant role, and that is what we are going to explore, what are the fastest transient technique that can be applied for a given switching frequency or a given converter. Now, there can be simultaneous, that means the load transient can happen much frequently, more frequently. In dynamic voltage application, the reference voltage and the load can go together, change in, because we are talking about a DVS enabled system where we need to optimize the dynamic power. So, when suddenly one task requires a certain voltage level, so we need to change the voltage. Suppose if the voltage requirement is high, that means the task is more intensive and we need to finish within a deadline. So, that means the load is already high, and as well as we need to increase the reference voltage. So, there can be simultaneous step transient, and at the same time we need a very high energy efficiency, because we generally consider efficiency at steady state, but those are steady state efficiency. But if converter undergoes very frequent transient, then steady state efficiency is not sufficient, because if we can optimize the transient performance, we can save the driver loss and other stuff, so that we can also achieve high energy efficiency for a longer duration. over a time period of time. The implementation simplicity, that means our switching control law should be simple to implement, because we will target for high frequency application, and also we have to, because the motivation, another motivation is that we are trying to explore the switching control law which can be applied in commercial product, and this can be used for very high frequency application. So that is why the control logic should be simple. It should not take much resources out of the, because ultimately it comes in terms of price. So if the control logic is complex, then it may require more number of transistor or the resources for the IC level, and that will increase the silicon area and that will increase the cost. So the complexity will come in terms of price and also in terms of power consumption. So we need to make the design simple, implementation simple. Another important, since we are talking about the switching control law and we are going to visualize from the large signal point of view, so we need to ensure that the system should be stable, not in terms of, there are different type of stability, and we talk about small signal stability that we discuss when we consider transfer function based approach, where we talk about gain margin, phase margin and so on. But here we are not talking about small signal. So in this context we are not talking about small signal. There are two more stabilities, the large signal stability, that means the system should not collapse, and this is very important particularly for boost as well as the non, I will say the indirect power converter, power transfer converter, where initially we take the energy in the inductor and then we transfer to the output side. So if we do not take a proper care, it may so happen, if the large signal it is unstable, the whole system can collapse and it can burn, like the inductor can saturate and it can damage your devices also. So you have to be very careful. And we also talked about fast scale stability, that means at steady state we should not end up with subharmonic oscillation. So because that will increase the ripple parameter, that will degrade efficiency, and that will also degrade the power spectrum, because it will make design of the input filter very complex. So we need to keep these are the motivation. And finally our analysis, what we are doing with phase plane, that should be very simple, so that we can visualize that how trajectory move and how can you link this trajectory to our control law, as well as can we link some of this switching logic with our conventional PID controller, which we traditionally use and which is very much well known. So these are the objective in today's lecture. So we will start with the boundary control for time optimal recovery. Okay. So what is that? Let us consider a buck converter. Here our Q is the gate signal and which is a controllable gate signal. Again we are assuming ideal one, but you can always consider the dead time, practical parasitic, and that we have discussed earlier, but here we are trying to build the concept fast. So the objective here, we need to turn on and off this controllable switch, because the other switch ideally is the complement of this high side switch, but practically there will be a dead time. So our objective to generate this on time and off time of this control S, the controllable switch, which is the high side switch for a buck converter, and it is the low side switch for a boost converter, because that switch you are going to control. So we need to generate a set of on time and off time. What are the objective? And this was initially investigated first, that how can we synthesize this set of on off trajectory and set of on off time using the trajectory information, which will result into time optimal recovery. So the objective is to find the set of timing parameter to achieve fastest transient recovery, and it turns out to be that it is simply a bang bang control, on off control, and you can achieve the fastest recovery by one switching action, and that was first reported in that Wilson and Burn, that in that paper Burns and Wilson initially they have investigated, and it turns out to be, if we take let us say a buck converter, and we will soon see how can we visualize this phase plane behavior into time domain behavior. So here the blue line indicate the on state trajectory. So I would say the blue one indicate on state trajectory, and the red one indicate off state trajectory. Okay. So, now the objective, suppose initially it was with the load current I0, that was our initial load current. Now suddenly there is a load step transient with a step size of, here it is delta I0 is the step size, that it undergoes a load transient with a step size of delta I0. Now the question is, when it was in steady state, you can find that the on state trajectory is on for certain duration t on, and the off state trajectory is activated for the duration of t off. So, we need to choose this on and off duration under steady state in such a way, so it meet the regulatory requirement, because you can see in the x axis we have taken the output voltage and the y axis we have taken inductor current. So, for the, because we know for a buck converter the average inductor current, because we are talking about synchronous buck, is nothing but the load current. So, for a given load demand, we need to ensure that the average value is Vref, that means that is my desired reference voltage. So, we need to set a set of on off time which ensure the voltage regulation at Vref in the average sense, which should achieve certain desired time period. That means one desired one requirement is a regulation of output voltage. The second one is a regulation of switching frequency, whether is it possible always to regulate or not, that we are going to see. But these two are sort of steady state requirement, that means if you make it, it will ensure that steady state. But apart from that, so this is like a steady state requirement, but we also have certain objective in the transient requirement, that means certain transient requirement. So, what are the transient requirement? What should be our on time for which the on state trajectory will be activated, and my off time such that it will only change its state once, it will only change its state once. That means this is like a one switching action. So, first it will turn on for this duration and then it will turn off, and eventually in one switching action it will come to the next operating point, and here this particular width is nothing but our current ripple, and this particular width if we take is nothing but our voltage ripple. So, that means again in one switching action it will come to steady state with its desired current ripple and desired voltage ripple. So, the desired current ripple and the desired voltage ripple will be determined by the switching frequency or the values of the on off time, and their ratio will decide your regulation, that means where we are going to regulate. But during transient we are not going to talk about regulation, because we need to choose the right on off time such that the trajectory after one switching action it will come back. So, the question is, it will be very difficult if we try to do by timing based control, that means exact calculation of the time. The only thing, this concept is well proved that one switching action will lead to time optimal recovery. But if we have more number of switching action, then definitely you will actually deviate from the optimality condition. So, then it is under certain constraint. That means suppose here one of the problem is that you will have a current limit, suppose there is a current limit. Then what you can turn on here and it will go like multiple switching action, finally it come back to here. Okay, so that means so that part we will discuss in subsequent lecture under constraint on the current limit, because this you can see there is a high current overshoot. So, this is my current overshoot. Sometimes this current overshoot may not be acceptable because there can be some limit in the inductor, but in generally these current limits are okay. But even if you put a limit, and we have to devise a control strategy where it will not allow the inductor current to go beyond certain value. So, that means there should be some kind of current mechanism, current control mechanism. Similarly, under the limit, what could be the performance and how it will deviate from the optimality performance. But it is clear, if there is no constraint, then one switching action will lead to fastest recovery, which is called time optimal recovery, and that was reported in 1978. Now, how to achieve the boundary control? So, using boundary control, that means now the objective is that we need to think of some kind of switching boundary, because we have discussed in sliding mode control. So, we need to think of some switching surface, and what should be the surface, what should be the switching parameters. That means we know that switching function like a sigma is a function of states, and then there will be some parameters. So, what should be the choice of parameter, what is the control law? So, all this we are going to explore. So, understanding phase plane behavior. So, in the last slide we talked about phase plane behavior, but I told you that we need to choose certain on off time so that you can meet the steady state ripple voltage and the steady state current ripple requirement. So, that is our steady state requirement, which will, because this is important in order to ensure that my EMI or my power spectrum is set in certain discrete frequency, so that I can design the input filter properly. Similarly, it is the limits, the ripple should be within the specified limit, so that because that will decide the power stage design, the capacitor design, inductor design, and so on. So, this is a time domain behavior. And how can we relate this time domain behavior into phase plane? So, if you draw the output voltage in the x axis and inductor current in the y axis, then you will see that this is the one which I have shown earlier. That means, this is under steady state, this is my on state trajectory. Okay, so, I can use red color. On state trajectory is this, and this is my off state trajectory. Okay. And as I said, if you take, this is my phase plane, this is my phase plane, this is the phase plane behavior. This one, and if we extend this, then this is the current in time axis, this is my time axis, this ripple is corresponds to this ripple. Similarly, if you expand in this direction, so this is my voltage axis and this is my time axis. Okay. So, you will set this is my current ripple, how it is going. Okay. So, depending upon trajectory. So, you can visualize the phase plane behavior in time domain, and it will look like this. So, phase plane to time domain relation in a buck converter, current ripple and voltage ripple. Now, if we, as I said, so you need to generate a set of T on and T off. For ideal buck converter, your output voltage V0 by V in, we know that it is the on time by total time, on plus off. Now, this, because we are not talking about the practical parasitic, and we already discussed that this is something like a equivalent to duty ratio, right? And we have discussed this ideal duty ratio makes sense when you are talking about the ideal converter, but in reality the converters are practical, and we also know the practical duty ratio is a function of load resistance, then DCR, equivalent resistance, which consists of DCR plus the RDS on, that we have already discussed. But if we talk about an ideal converter, the duty ratio is nothing but the ratio of the on time by the total time. Now, you can reduce this on time, similarly you have to reduce the off time, so that the ratio remains same, because that will decide my regulation point. If we reduce that, then we can reduce this ripple. As a result, consequently, so in time domain it will look like this. So, suppose we are talking about in one scenario like current ripple like this, and this has an average value of this, and in the other scenario we are talking about something like this. something like this. So, the average will remain same, but we have increased the switching frequency, the ripple has come down. So, these are the faster and slower switching frequency. Now, we want to recapitulate our sliding mode control concept in a buck converter. So, what we did in the sliding mode control initially, if you go to our lecture number I think 46, we will find the first state variable is that means the previous lecture was voltage error. So, you can take Vref minus V0 or V0 minus Vref. So, I have taken x1 to be V0 minus Vref and x2 is the derivative of the error voltage. So, now we are talking about selection of switching surface in sliding mode control that we have discussed. So, this sliding surface we have considered, what are the state that we have considered? We have considered x1 to be V0 minus Vref, right, and what is x2? It is nothing but x1 dot. That means, in the sliding motion where sigma x, we know we have taken k1 x1 plus x2 equal to 0. Since x2 equal to x1 dot, it will be k1 x1 plus x1 dot equal to 0. So, from here we can find out x1 equal to x1 0 into e to the power minus k1 t, and where k1 is positive and here it is minus k1, the slope. And we have discussed for different value of slope, the slope can be higher or slope can be smaller. Here it is a smaller slope. The smaller slope will result into overdamped system, and we have already discussed in the context of sliding mode control that the sliding motion, or if we have also discussed about the boundary control concept that we are going to take. So, it will be like a reflective region, that means both side the trajectory will be towards the switching surface. So, it will have kind of overdamped response for smaller k. If we increase the k, then we have also seen that this will lead to some overshoot, undershoot and then sliding motion. Okay. So, now our question will be how to select this k1, that is one of the question, and by selecting k1 can we achieve something close to the time optimal or not. So, that means first we have to consider the trajectory, first we have to understand. So, here if we take the on state dynamics and if the on state trajectory move along this path, then it is going towards the switching boundary. If you take the off state trajectory, and if the off state trajectory, whether is it coming towards it or is it going away from it. So, if depending upon that there can be many various condition, whether both side the trajectory on off trajectory are towards the switching boundary or one side it is towards, the other side it is away, or it can be the third possibility, both side can be away. So, these concepts are actually explained in Elements of Power Electronics book, and if we classify, that means as I said this is my switching line which is equal to 0, these all should be equal to 0, then the trajectory will be towards in one side, the left side, it can be right side, trajectory is going towards the switching surface, but that is my on state trajectory, but my off state trajectory is going away from it. So, that means this is called refractive point, and such kind of concept will be used to achieve time optimal recovery. But if both side trajectory are towards the switching surface, then it will slowly kind of you will achieve the sliding motion. That means the trajectory will chatter and it will go towards, let us say if this is my origin point, it will go towards origin. Okay. So, that means both side then the chattering will start, the actual switching will act. And the third possibility, if both side trajectory are moving away, then that is called rejective region, and we must avoid such region, otherwise it will be unstable. So, that means the rejective region we should not place a switching surface, or we should not consider a sector of two dimensional plane where our surface is placed in the rejective region, and if you take any initial condition there, then your trajectory is will go unboundedly, and it can lead to, like particularly for a boost converter, maybe complete collapse of the system, or it can damage the other devices. So, the large signal stability in the refractive region, we can think of, it will take like overshoot, undershoot, but it will take more cycle, and unstable in the rejective region, right, and in refractive region it is stable, but it will be overshoot, undershoot, and the unstable case in the rejective region. And the reflective operation, so in the refractive region also, if you do not take the sequence of switching properly, it may so happen that you start with on time and then off times. That means if you choose a wrong control logic, then it will become unstable. So, that means the only refractive region is not sufficient, the switching control law is also important. What kind of control law you are taking? In the reflective region, both sides the trajectory are approaching. So, that means it will slowly move towards this line, and you can actually create a hysteresis band, so that it will like this. So, it is your switching surface both sides. So, the trajectory will move like this, it will move like this, it will slowly move like this and going towards the desired point, and there actually we achieve sliding motion. So, now here we are considering, we are going to implement current based this surface, the switching control, where one state is my inductor current minus the output current. So, whether you will consider output current or something else, that we will see. The other state will take output voltage error. So, our switching boundary, again the current error plus some gain into voltage error, and this is something similar to a proportional gain, because this looks like your IL minus I0 plus Kp into V0 minus Vref, right. We can rearrange in a other way, we can write in an alternative way, we can also write alternative way, we can write I0 minus IL plus Kp into Vref minus V0. So, if you multiply with a minus sign here, as if we have multiplied with a minus sign to get there, because it will look like actual error voltage, then our switching control has to be accordingly modified. Otherwise, as I said, it will go into rejective region and the trajectory will move away. So, these two control logic should be just the opposite, because we have taken. So, you can use any of them, but accordingly you have to choose the switching control logic. Now, the red one is the one which is represented by this surface, but if we use this surface and if we design the control law in such a way, okay, this is my switching logic, sigma equal to 0, and if we force the trajectory like reach there, if we force the trajectory that you reach there, once you cross it, then you come here. So, if you do like this, then it will result into infinitely fast switching. And this is known as chattering behavior, right, chattering, and that we must avoid, because if there is any chattering, because we are using a practical converter with practical switch, so it will force the device to operate at its hard limit, turn on and off very rapidly, and it can damage the device, and it can, so we must avoid. That is why we need to incorporate a hysteresis band, so that this will introduce a dead time. That means, once you turn off, you provide some time and then again it will turn on, and this can be either implemented by a direct time based control, like we will discuss in subsequent lecture, or it can be introduced by directly on the trajectory by means of a variable which is a hysteresis band. So, that means we can introduce a band, and this is usually that in case of hysteresis based implementation, and if we introduce a time, then we can think of a constant on off time implementation, where we are putting a time dead time. Okay. So, the steady state behavior sigma x. Now, if we want to implement our ideal switching surface, and you see, since we have taken x1 to be IL minus I0 and x2 to be V0 minus Vref. So, this is my IL minus I0 and this is my V0 minus Vref, and then we have a Kp here. So, this is my proportional controller and these two are added up. So, these two are added up and this is my sigma x, right. So, this is my sigma x. Now, what is our switching logic? Here the switching logic is this: Q will be equal to 1 if sigma x less than 0, or it is 0 if sigma x greater than 0. That is my switching logic. Because that means this side I will take Q equal to 1 and this side I will take Q equal to 0, and this is my switching logic. And this we can implement using MATLAB, but you will find real difficulty because you have not inserted any hysteresis band and you are forcing your computer, if you want to simulate, to operate or compute at the hard limit, because computer will have a finite step solver time. That means the time has a minimum resolution, so it will try to hit the limit because it will continuously turn on and off within this limit, and that will slow down your whole simulation. So, the ideal switching logic is practically not recommended to use. It results into very fast switching at steady state, which is not desirable. It can damage the switch, and it limits, there are limit on the practical on off time of the device. Even for simulation also we have a limit because of the simulation step size, and in practical converter this can lead to component failure because of heating effect, and you are turning on and off very rapidly. And first of all, this may lead to very like a chattering behavior will lead to EMI problem, because even if we put a smaller hysteresis band, then the switching frequency can be very high. So, we need to set the right hysteresis logic. So, adding a hysteresis band, suppose as I said, we have chosen this sigma x now divided into two parts. One is sigma 1x, which is parallel line on the top, and the other is sigma 2x, which is a parallel line on the bottom, because these two are parallel line and they are separated, and the sigma 1x is crossing this x1 axis at A point and sigma 2x is crossing x1 axis at B point. So, we can write, and we need to find what is the equation. We know that sigma x is equal to x1 plus Kp into x2, and that equal to 0. Now, sigma x, certainly it is a parallel line and sigma x is passing through origin, but sigma 1x is not passing through origin. It has parallel line, but it is, that is why for sigma 1 is we need to add this offset, and you see all these parameter will same because it is a parallel line. Sigma 2x is the same parallel line, but it will have a different offset because it is here. And how to find out this offset? So, at point A where sigma 1x intersect equal to, and that is already equal to 0. So, at point A x2 equal to 0, and if you substitute here, and at point A x1 equal to A, that means at this point you are getting x1 equal to A and x2 equal to 0, and if you substitute you will get C equal to minus A. Similarly, at point B, if you substitute, what you will get x1 equal to B and x2 equal to 0, so you will get C equal to minus B2. Now, suppose x1 axis is my current axis. So, I want to introduce a current hysteresis. Upper limit is delta IH by 2 and the lower limit is minus delta IH by 2. So, that is why I substitute A equal to this and B equal to this, and then if we put it into our earlier form, because you saw what we are getting is here C1 equal to minus A, and we substituted A equal to this. That means we have to first write down what was our sigma 1x? It was equal to x1 plus kp x2 minus 1, and that is equal to 0, and we found sigma 2x is equal to x1 plus kp x2, and you can see it is minus b equal to 0. Since we are taking a equal to delta h by 2, we are substituting here, and b equal to minus delta h by 2 is substituted here. So, we will end up with these two equations, right, these two equations. And then what will be our switching logic? That means our switching logic will be, since you can see what is the requirement, that means your this side trajectory, our sigma 1x for q, what is my q logic? That means if the trajectory cross this, that means when sigma 1x is greater than 0, then we should turn off the switch, right. That means sigma 1 is greater than 0 is nothing but, if we write it here, sigma x is greater than delta h by 2, and similarly sigma 2x should be less than minus 0, and which will lead to this equation, because the offset trajectory when it hit here, we should turn on the switch, right, we should change the logic. So, now we are going to implement how to implement the practical switching law. So, we saw the ideal switching law, q equal to that means the q equal to 1 if our sigma x is less than 0, and it is 0 if our sigma is greater than 0. So, this will be modified to q equal to 1 if sigma x less than minus delta h by 2, and it equal to 0 if sigma x greater than delta h by 2, and that we have seen in the previous lecture, okay, previous slide. So, here sigma x. So, this difference actually if I take the difference here at any point, this difference is nothing but or delta h by 2, because we are setting this band here, okay. So, it is a current hysteresis band. And how to implement? Again the control law, sigma x, what is this? Here we know the sigma x is in our case IL minus I0 plus Kp into V0 minus Vref, okay, that is sigma x. And then we are adding this band, and that we have discussed, that means sigma x minus, that means what was our sigma 1x? It was sigma x plus, if we go back, what was sigma x? This is my sigma x minus delta h by 2, and this is my sigma x plus delta h by 2. That means, so this should be minus, that means we should choose this to be minus delta IH by 2, as sigma 2x is sigma x plus delta IH by 2. So, you can see this is my sigma 1x and this is my sigma 2x, and they are compared with the hysteresis logic here. So, this is a hysteresis logic. That means, what we got, q equal to 1 if sigma 2x is less than 0. You see, this is the logic that it will set, it will become 1, and it will be 0 if sigma 1x is greater than 0, and this is a logic, okay. So, we can implement this logic, and we can realize this logic. Now, we want to show, I want to show the MATLAB implementation. So, I did a little different way in MATLAB. What I did, here again a sliding mode controller, again this is my reference voltage, we can apply a step, this is for step transient I can do, this is my reference voltage, and I am taking the output voltage. So, this block I have presented multiple times that we have developed. So, it is known. This controller we are going to discuss how are we going to implement this controller. And you can see there is this Iref I have chosen to be load current. So, this Iref I have chosen, it is nothing but load current, but it is not necessary, you have to choose the load current always because there are alternative way of representation. And I need V0, so this is my V0, Vref, this is my Vref, IL, this is my IL, and Iref, this is my I0, right. So, if we go to the next what I am doing, here I am using a different implementation. So, here you can say this band which is my delta IH by 2, the same band delta IH by 2, delta IH. You can implement the way here I have explained, no problem, but I have implemented in a different way. So, I can change this way and do it whatever it is there. This transfer function is a controller, and typically I am choosing this to be a proportional control because here I want to put it like a standard the voltage loop error voltage. So, this is my error voltage. In this case I have used a conventional notation of error voltage V0 minus Vref minus V0, then it is going to a proportional controller, and then we are adding this band and actual current. So, I have taken here. So, this current, that means I have broken this sigma x into two parts. So, in this implementation this particular signal is nothing but your Kp into Vref minus V0. That means, if I talk about sigma x, which is my IL minus I0 plus Kp V0 minus Vref, and that at 0 we want to achieve, right, that is equal to 0. So, if I take this part, that means IL minus I0 is equal to minus Kp V0 minus Vref, which is nothing but Kp into Vref minus V0, and this is exactly I did it here, okay. And I kept IL minus I0 here. So, this term is my this term here, and then I have added the hysteresis band with this quantity. So, that means you can implement in different way, you can try it out in MATLAB, we have explained multiple way. Now, I want to show the simulation result. So, I just want to go to MATLAB simulation. So, first I want to show you that this is the implementation that I have just discussed. So, this gain I am setting from externally, and this is the logic, numerator denominator, and this is my band, and if you go to top block, this is my realization. Now, I want to go, so this is my buck parameter. You can take an ideal buck to start with, you can put all the parasitic to be 0, there is no problem, okay. So, you can take all the parasitic to be 0, all the parasitic to be 0, okay, and 12 volt input, 1 volt output, a standard form. And here you can, this alpha is not required. So, you can remove this path, only load resistance should be sufficient. We do not consider ramp, so it is not required. So, poles and zeros are also not required. Now, though I am showing a controller, it should be a controller rather than PID. So, this Kp I am choosing 60. So, forget about Ki, Kd and Td because I am initially interested in only proportional control, and I have chosen Ki to be 0, and here I am using a surface, I just comment it, this is the control logic I am taking, okay. So, you can keep it somewhere else just to avoid any confusion, okay. So, I can take this thing, put it at the bottom because I may not need it. So, this part when I require I will put it. So, I do not need any Kp or Kd, okay, and here I am just considering, yeah. So, I am not considering any integral action, it is just initially a proportional control and I am applying a load step transient of 20 ampere. So, initially my load resistance was 100 ohm, that means my initial current was 1 volt by 100 ohm means 10 milliampere, and that is changing, the current is changing from 10 milliampere and it goes into 20 ampere, okay, and we want to see the response. So, let us see the response for this scenario. So, now this is the phase plane behavior. So, this is my output voltage axis and I am not consider any integral action, and you can see it is going first transient here, this is the inductor current, and then it takes multiple switching cycle before coming back. And if you go to the output voltage waveform, because I have discarded some of the initial transient because we want to show the phase plane correctly, you can see it is taking, like initially it is turn off coming here and then it takes some more cycle before it goes to steady state. Since I have not considered any integral action, that is why there is a steady state error. You can see the average output voltage is not exactly 1, slightly above 1. Okay. What is the current waveform? If you see the current waveform looks something similar. Okay. So, this is the current waveform. Now, I want to reduce the gain and see, suppose I want to use, let us say the gain to be 20, very smaller gain, and I want to see how does the response look like. And you can see it takes many cycle to reach there, many cycle, and it is evident from here that it will take multiple switching cycle to reach steady state, multiple. So, it is kind of overdamped system, and this is something similar to what we discussed in this particular scenario in sliding mode control, where we have considered, so here a smaller gain. So, it will be overdamped response, more number of cycle it will take. Okay. But we also want to see, that means it is totally in the reflective region, where if you see that okay, so practical switching law, yeah. So, if we see the response, the phase plane, it is like a sliding mode. So, it is taking more number of cycle, it is like overdamped. After turning on, it is taking more cycle and it is coming steady state. Now, what will happen, and there is no almost current overshoot. So, current overshoot is substantially reduced, but it is taking longer duration. Now, if we increase to let us say 100, so instead of, so let us make it 100 and see how does it respond. So, make it 100, it is slowly coming, if you go and check the response. So, you will find there is slightly overdamped. That means it is not exactly one switching action, like it is taking, like here it is taking few more cycles to reach steady state. That means it is very, like small transient is coming here and the response is almost near to optimal response. Okay. Now, if we reduce further, let us say we make it, let us say 95 or so. So, by that way we will come almost close to the optimal response. We are almost close to the optimal response and we can further change the gain and see how does it look like. That means we are playing with the gain and we are, yeah. So, I think it is, we should make it 97. Okay. So, it is going close to that. So, that means it is almost reaching steady state in one switching action, and you can see it is going on, then turning off and it is reaching here. Okay. So, if I want to change this portion, so you will find much better, yeah. So, one switching action, and this is a lobe it is created like on off operation. Okay. So, that means now if we further increase the gain to let us say 130, 120, suppose we have chosen a very high gain, then you will find there is a high overshoot undershoot. In the output voltage you can see there is a high overshoot in the output voltage. So, which is that means we have not selected the slope properly. So, it is a slope selection. Now, that means if we make close to 100 and now if we initiate the integral action, that means let us have the integral action and then we see what happens. So, that means what we are considering here, because of integral action it is slowly coming to steady state, and if we increase the integral action, let us say this, so we are getting close to steady state action. So, because of integral action the voltage will slowly come average voltage to be 1 volt. Okay, so like a 1 volt. So, that means the integral action if we add, that means if you go back to the switching surface. So, here our sigma x I am considering the sigma x is IL minus I0 plus Kp into V0 minus Vref plus Ki into V0 minus Vref into dt. So, this integral action we are just incorporating and that will act very slowly, so that our steady state error can be eliminated. Okay. Alternative way, if you do alternative way using voltage, that means if you go back to the sliding mode control using voltage and the derivative of the voltage here. So, in the earlier representation, earlier realization, we need load current information as well as the inductor current information. But now, we want to get rid of this load current and output current, that means sorry, load current and the inductor current, we do not need to sense load current and output current. So, we are taking the error voltage as the one state and the derivative of the error voltage to be the second state. And if you do that, then we can realize this already we have explained in the sliding mode, that we can write x1 dot x2 dot realization with the switching control logic. And we have also discussed what should be our switching control logic, so that we can satisfy the reaching condition and the sliding condition. So, the implementation here is different. See, I have not used any inductor current, neither there is any load current. So, it is only output voltage and the reference voltage, right. And inside I am using a voltage band rather than current, because there is no current here. The voltage hysteresis band, and here again I am setting. So, that means this is like your error voltage, where the error voltage is, I have taken here Vref minus V0, and the controller here now it is something like I am taking like a PID controller. So, I will tell you that this can be very easily linked with a PID controller. So, where this controller will have 3 components, that means you can think of, if this is your something like a sigma dash x. So, sigma dash x, I am taking the first state to be my, let us say, Kp into Vref minus V0. Another state I am taking Kd into ddt of Vref minus V0 plus Ki into Vref minus V0 into dt. But we should remember, I am not using a direct derivative, I am using a band limited derivative, and we have already explained the PID controller, right. So, and that will discuss, that means actual whatever I am considering here is like a standard PID controller, Kp plus Ki by S plus Kds by tau ds plus 1, PID controller gain. Okay. And how to choose this Kp, Ki, Kd, that we will discuss, but here I have chosen the time to be very small. I have chosen the switching period by 20, because then we will get close to a derivative action. I have chosen here K derivative to be C, because we want to link this PID controller look like a switching surface, that we will discuss in the next lecture. And this is my output capacitance. Output capacitance, Ki choice is somewhat flexible, but the Kp choice is the one which will decide the transient performance. And the selection of this delta V H, which is the hysteresis band, and this is by 2 here, that will decide our switching ripple, that means the steady state switching frequency. So, let us go back to our MATLAB and see what happened if we go to our voltage based controller. So, this is my voltage based control which I have explained here, V band, and this is a transfer function that we are defining from inside. Here we have already discussed that we have not used any voltage or current, load current, neither load current nor inductor current. Now, we want to set, that means we want to bring back our this logic, that means this was the logic of our PID controller. So, here we want to consider, so we want to stop here this part, comment here. Okay. So, you can see the derivative again I said it is the capacitor voltage. So, it is TD by 10. So, you can take TD by 20, there is no problem. And then numerator and denominator I have set. Let us see how it happened. In the simulation file I have to change the VSM because this file name is V. Okay. So, the band voltage band I have set 1 hysteresis because to achieve the desired value. So, let us see what happened. So, this is my voltage based realization, there is no current realization here, but you can see it is taking more number of cycle to reach steady state. That means, it is not optimized or it is not the optimal performance. So, you need to increase, but there is also steady state error. So, first let us see what should be our Kp. So, if I set Kp to be 80 for example, then we will see that we are getting near to optimality condition, but still it is not exactly coming to the optimal. That means, it is still slightly over damped. So, we can further increase the gain to let us say 85, and you will see that it is almost coming to steady state, but there is a steady state error because it is shifted by almost 10 millivolt, and we need to, if we want to eliminate, let us enable the integral action. So, then it will make sure that there is no almost steady state error. Okay. So, we have enabled the steady state error now. So, it is coming back and we are coming close. So, we can further increase because, so we can do like 90. So, because it is taking here, because of the integral action, it is slowly approaching and finally it is reaching steady state. So, more number of cycle. So, you can eliminate some of the data here, or if you make it 10, yeah. See, the derivative also has a role, that is time constant. So, if we limit the band of the derivative, that also lead to, so that means the derivative filter time constant also play a significant role. So, this part we will discuss. So, the optimal transient scenario and the MATLAB case study we have shown that close to optimal, the choice is the proportional gain is very important. This play a significant role in the shaping the transient response. Now, second order switching surface, because here we have taken first order switching surface, but first order switching surface we need to optimize Kp, otherwise you will end up with either under I will say under damped behavior or over damped behavior, or there can be high overshoot undershoot. So, the choice of Kp is something which is we need to really take care, otherwise this may not be a good solution in terms of optimal response, and that is one of the objective in this course, that if you frame it into a PID controller and if you can derive this optimal gain, then first order switching surface is sufficient. But if we consider a second order switching surface, the boundary control, where we want to take the desired switching surface which is almost taking the shape of the off state trajectory. That means, the term boundary control comes, that means if we set the switching surface close to the boundary of the trajectory or basically the desired trajectory, then we can get optimal response, right. So, here the second order switching surface is better in compared to first order, which takes somewhat closer to the desired trajectory, because you can see the green one is the parallel line to the actual dotted line, the second order surface, and the red one is my off-state trajectory. So, that means my red one is the off-state trajectory, though they are not exactly equal. So, I am talking about this green one and I am talking about this one. So, they are actually away, they are slightly different, but it is far better than first order. So, then it was proposed that if we take the second order switching surface, then you can achieve close to time optimal performance without much changing of the parameter by only considering by changing input voltage output voltage scenario. You can achieve close to optimal performance, and here also you need to incorporate the load current, because for resistive load this is my load current, for resistive load is V0 by R, for current load it is I0, right. So, this second order switching surface can achieve close to optimal performance. So, here also you need to sense the load current, okay. So, now higher order switching surface, so second order switching surface can go close to optimal performance for a given parameter, which depends on the input output voltages and characteristic impedance, and this is generally set from the design, okay. But the implementation require load current for this case. Second order switching surface, then the raster switching surface, which in this paper it is compared the performance using different switching function, that means first order, higher order, and then it has proposed the switching surface which is computationally effective and can achieve close to optimal behavior. The other one is the natural switching behavior, where if we, because our desired one we want to achieve the target trajectory, and that can be achieved by if we normalize the state variable with respect to its operating point, and if you do that, then you can achieve perfect time optimal control, but the implementation may be slightly difficult because you need to normalize the parameter, but these techniques are also very effective. So, all these techniques, higher order natural switching surface can lead to time optimal performance for arbitrary transient, all these scenario. So, the many other switching surface exist which can achieve very fast transient response. Now, the choice of switching surface, the first order surface, we saw it is the simplest to implement, but it requires slope optimization or basically the optimization of the Kp, that is the question, okay. But it is very simple to implement. So, in high frequency application this technique may be useful because it resembles something like a PID controller, and that we are going to discuss more in detail. The second order switching surface or the higher order, it requires more resources because you need to create a square block, and you need to also incorporate many other, if you go back these parameters, you have to plug in this parameter. This is useful, but in terms of resource wise this can consume more resources, and also it need to sense the load current, right, requirement. Natural switching surface is also very effective technique, but again it requires normalization and it may require more resources. So, these techniques may be useful when you are talking about maybe few hundreds of kilohertz switching converter, maybe for high power, but when you are going for megahertz switching frequency or maybe 500 kilohertz or more, then you need to optimize, or particularly when you are going for power management IC where the resource play a significant role. So, our choice, the question is that is it possible to achieve the fastest response using a first order surface only? If we can do that, then it is the most it is the simplest one and structurally similar to Kp, Ki, Kd PID controller, and which are often used in any high frequency PMIC or DC-DC converter. So, we need to take the advantage of that existing PID controller, and we need to frame that PID controller into a switching structure first order, and then we have to calculate the gain, and we need to find out how this gain can be optimally tuned by incorporating the switching information. So, we need to link the PID control technique with a PWM control and PID controller linking with the, I will say the switching surface, the linking with the switching surface. We need to link with the switching surface. So, this is the link that we are going to see. If we can do that, the first order switching surface link with this PID controller and link with the PWM control, then our traditional PWM control, whether it is a current mode or voltage mode, can be tuned to achieve the fastest time optimal response by formulating using a first order switching surface or something similar. So, with summary, we have discussed switching control and the trajectory in switch mode power converter. We have discussed the switching surface in sliding mode control. We have discussed the boundary control concept on trajectory, and we have also discussed in sliding mode control. Actually, the boundary control is a subset of sliding mode control where we want to design the surface in order to make the surface look like a target trajectory. But by doing that, we are going for higher order switching surface, and that surface can be more intensive in terms of resource requirement and in terms of complexity. So, our target is to make the design simple and achieve something optimal and use the PID controller structure we want to exploit, and we have also discussed a few MATLAB case study. So, with this I want to finish it here. Thank you very much.